Hello everyone. In the previous video we built a working Cython module and learned how to compile and import it from Python. But the working Cython module is not always an optimized Cython module. In this video we'll focus on how to make Cython code faster in a more systematic way. We'll use type declarations, timeit benchmarks, and Cython annotations HTML report to find where Python overhead still exists. The goal is not just to write Cython code, but to understand whether that code is actually running efficiently. Let's start with a baseline benchmark. Here I have a simple Python function called compute_score. It receives a sequence of values, loops over them, performs a small numerical calculation, and adds everything to a running total. This is a good example for Cython because the function itself is simple, but the loop can run many times. Now let's create a benchmark file. Here I am creating a list of 1 million floating point numbers. That gives us enough work inside the loop to make performance difference visible. Here, timeit will call our function 10 times. I'm using a lambda so we can pass the existing values list into the function. The result is the total time for all 10 runs. Now let's run this benchmark and record the baseline. This is our pure Python baseline. The exact number will depend on your machine, but what matters is that we now have a reference point. Every optimization we make from now on should be compared against this number. Now that we have the Python baseline, let's create a Cython version and start adding type declarations step by step. The first version is almost exactly the same as Python function. This inside a POX file, so Cython can compile it, but we haven't really told Cython anything about the types yet. So values and even parts of the calculation may still be handled as Python objects. Now I'll compile this version using simple setup.py file. At this point we have a compiled module, but remember, compiled doesn't always mean optimized. Now I'll update the benchmark so we can compare the pure Python version with this first Cython version. This is important because we don't want to guess, we want to measure each step. First, I'll change my import so we can distinguish between compute_score of Cython version and Python version. Then I will copy this. This will be Python type. We choose PyCompute_score, and this will be Cython type. We choose PyCompute_score. And I'll add an extra import. Python time and Cython time. And we can try to run it. Depending on your machine, this version may be slightly faster or sometimes not dramatically different. In my case, the result is almost the same with Python version and Cython version. Now let's start adding type declarations. First, I'll change def to cpdef and declare that this function returns a double. Double is a C floating point type, and it fits this function because our calculation works with decimal values. I'll keep values as objects for now, because at this stage we're still passing a regular Python list. Next, I'll type the local variables. Total becomes a C double, so updating it inside the loop is cheaper than updating a Python float object every time. I'll also declare x as a double. Now, when we loop over the values, Cython will convert each item from the Python list into a C double before doing the calculation. This still has some overhead because the list itself is a Python object, but the arithmetic inside the loop is now much closer to a C-level arithmetic. Now I'll recompile the module and run the benchmark again. Now we should see a clearer speed improvement. The exact number depends on the machine, but the important point is the pattern. As we add useful type information, Cython has more opportunities to remove Python overhead. But even with these type declarations, we still don't know exactly where Python overhead remains. For that, Cython gives us a very useful tool, the annotation HTML report. Let's generate it and inspect what our code is really doing. To generate the report, we can run Cython with the annotation option. The A stands for annotation. This creates an HTML file that shows our Cython code and highlights how much Python interaction remains on each line. Now we have a file called Cython HTML. Let's open it in the browser. This report is extremely useful with optimizing Cython code. The basic idea is simple. The more yellow a line is, the more Python interaction is happening there. Lines that are white or very light usually mean Cython was able to generate mostly C-level code. Here we can see that some lines are much lighter now because we type total and x as double. That means the arithmetic itself is closer to a C-level arithmetic. But the loop over values may still show Python interaction because values is still a regular Python object, in our case a Python list. If we click on a highlighted line, we can even see the generated C code underneath. You don't need to understand every line of this generated C code, and honestly, you usually won't read it in detail. But it gives us a clear signal. If a line expands into a lot of Python API calls, then that line still has Python overhead. So when optimizing, we want performance-critical loops to become as light as possible. We don't need the entire file to be white. We mostly care about the hot path, the code that runs many times. In our function, the hot path is the loop. The reports show us that the next bottleneck is not just the arithmetic anymore. It's how we access the input data. So now that the annotation report has shown us where Python overhead remains, let's optimize that remaining bottleneck. Instead of looping over a generic Python object, we'll move toward a more C-friendly representation of the data. Now that we looked at the annotation report, we can see something important. Typing local variables helped, but it didn't remove all Python overhead. The remaining overhead comes mostly from the fact that the values is still regular Python list. In this version, total is typed and x is typed, so the arithmetic is much better than before. But the loop still iterates over a Python object. Every time we get a value from the list, Python is still involved. This is a very common situation in Cython. You add types, the function becomes faster, but the annotation report shows yellow lines because some part of the code is still using Python objects. In our case, the bottleneck is the input data structure. The Python list is flexible. It can hold floats, strings, objects, anything. The flexibility is useful, but it means Cython cannot treat the list as a simple block of C doubles. So even if we declare X as double, Cython still has to take each item from the Python list and convert it into a C double during the loop. Now let's look at first optimization. One small improvement is to make the loop itself more explicit. Here I'm using an index-based loop, and I'm typing a loop counter as a pi size t. Pi size t is a standard C type used for Python container sizes and indexes. This gives Cython more information about the loop, but it still doesn't fully remove Python overhead, because values are still accessing Python lists. So this version may help a little bit, but it doesn't solve the main issue. The main issue is that our data is still stored in a Python object container. To remove more overhead, we need to pass data in a form that Cython can access more directly. And this is where type memory views become useful. A memory view lets Cython work with array-like data as a type block of memory. Instead of saying this is some Python object, we can say this is a sequence of doubles. Now let's rebuild our score Cython with new function implementation. And let's update our benchmark file. As you can see here, I updated the import to include a new compute score index, and also I added the index timeit. Now let's test the time execution. This is actually a good result, because it teaches us something. Not every type declaration gives a huge speedup. Typing the hot arithmetic helps, but if the data access still goes through Python, we still have a bottleneck. So now let's take the next step and use the type memory views, which gives Cython a much more efficient way to access numeric data. Now let's take the next step and introduce type memory views. In the previous version, we typed our local variables, but the input data was still a regular Python list. That means Cython still had to interact with Python every time it accesses an item. A memory view gives Cython a more direct way to work with a numeric array-style data. You can think of a type memory view as a type view over a block of memory. Instead of saying this input is just some Python object, we can say this input is one-dimensional sequence of doubles. That gives Cython much more information, and it can generate more efficient code for accessing the data. Now I'll create another version of the function called computeScore_memoryView. The important part is this argument. This means the function expects a one-dimensional memory view of double values. So instead of generic Python object, Cython knows that this is numeric data stored as a double. As before, I'll keep the accumulator as a C double. For the index and length, I'll use PySize_t, which is a correct type for Python style sizes and indexes. With memory views, we can get length using zero index item from values shape. In the loop that is similar to our previous version. But internally, this is much better because accessing values I no longer works like indexing a generic Python list. Cython knows the type of the data, so it can access the value much more directly. And finally, we return the total as a double. Now we have all the versions we need: the Python version, the type C version, the indexed version, and the memory views version. Next, let's update the benchmark and compare them side by side. For the Python version and the earlier Cython versions, I'll still use a regular Python list. For the memory views, I'll create an array of doubles using Python built-in array module. The D-type code means double. This gives us numeric data that Cython can view as type memory buffer. Now let's recompile one final time and run the benchmark. The pure Python version is our baseline. The type version improves things because total, X, and return value use C-level types. The indexed version gives Cython a more explicit loop structure, but it still accesses a Python list. And the memory view version usually gives the best result here, because the input data is now exposed as a type numeric memory. So in this video we moved from just writing a working Cython module to optimizing it systematically. We started with a Python baseline using timeit, then we added Cython type declaration step by step. We used the annotation HTML report and find remaining Python overhead. And finally, we introduced type memory views for efficient array-style data access. The most important takeaway is don't just guess where your code is slow. Measure it, inspect it, and optimize the parts that actually matters. Thanks for watching and see you in next videos.